Hey everybody, it's Ripley back again. I'm going to do a nifty little trick. I'm going to turn a function, as if by magic, I'm going to turn a function into a power series. All right, so I'm going to start with this function. F of x is equal to 1 over 1 minus x. And I'm going to turn this, like I said, as if by magic, into one of these guys. There's that, and this is going to be c sub n x to the n. Now, clearly, this is centered at 0. Okay, because otherwise it'd be x minus a to the n. Remember from last section. Now, the only tool that I have to do so at this point, and this is going to feel a little contrived in this section, but it also makes it a little more simple to be able to do to get your brain wrapped around, is the geometric series. Now, let's review real quick about the not the geometrics, be an excellent geometric series. All right, remember, geometric series is a series of the form n equals 0 to infinity and a times r to the n, and we know that this guy converges, if it's going to converge, converges to a over 1 minus r, and it converges if absolute r is less than 1. Now, this r isn't incidentally created, by the way. We have experience from 8.5 with power series. We know that this is a radius. Think about that. That is also a radius of convergence. It's here around which it converges. All right, so here we go. If the only tool that I have is the geometric series, and I look really close, look at, change pencils, or change colors real quick. Look at f of x equals 1 over 1 minus x. Well, doesn't it look the same? It looks exactly the same, doesn't it? I've got an a, so if I were to let a equal 1, and I were to let r equal x, then doesn't that imply that, I mean, look at it, it's in the perfect form, that I should be able to write 1 over 1 minus x as the sum, as n goes from 0 to infinity, of a, which is 1, over 1 minus r, which is 1 minus, a, which is 1. You got to watch me on this one. A, which is 1, I just rewrite the thing. No, that's not how it works. 1 times x to the n, because that's what r is. So this turns into the sum, as n goes from 0 to infinity, of x to the n. Now let's write a few terms out. My first term is going to be 1 plus x squared plus x cubed plus dot, dot, dot. It goes forever. Now you're saying, Ripley, there is no way. This is a rational function. This is a polynomial function. There's no way that that can be true. Well, careful. Remember, the radius of convergence for geometric series is like r, absolute r has got to be less than 1. And since r in this case is x, this is true when absolute x is less than 1, which implies that x is between -1 and 1. This guy right here is my radius. This guy right here is my interval, now that we know how power series work. You may be saying, well, Ripley, what's c sub n? Well, it's 1. I'm not afraid of that. Now, if you don't believe me, watch this. There's something sort of special that's going to happen here. Let me see if I can get into this guy. All right, so I have already put in 1 over 1 minus x. You got to be real careful. Make sure that you get the parentheses in this guy, because if you don't, you write this as 1 divided by 1 minus x. The computer's going to divide by 1 first and then subtract x, and it's going to turn into negative x plus 1. So watch. I'm going to graph this thing. Let's have a quick look-see. I already tweaked my window, made my window from -1 to 1 because that's my interval of convergence. I'm going to graph it. So here's the function. It is right there. Now, watch this. I'm going to put a few terms in. I'm going to put, well, let's go with 1 first and just graph it. Watch. Oh, look at that. All right, so here's my curve and then my horizontal line. Those two aren't equal at all, Ripley. You crazy. Well, the only place they are equal, I guess, is at their center. They've always got to be equal at their center. So when x equals 0, 1 equals 1, right? So let's put a few more terms in and see what happens. Maybe it's just because we're grabbing that one term. So let's go. I'm going to go 1 plus x squared. Because as of now, I'm not real impressed. But watch. All of a sudden, there's my function, 1 over 1 minus x. And then all of a sudden, look at that. Check that out. Now it appears as though from here to here, we're pretty darn close. And that's only 3 terms into this thing. Let's throw a few more terms in there. I'll go out to like x to the 5th or 6th. Depends on how ambitious I'm feeling. So I'm going to go, come on, what's going on here? Go, move. Plus x cubed plus x to the 4th. We'll go out to the 5th because this is going to drive me nuts. plus x to the fifth. And we'll see what happens. Plus x to the fifth to the fifth. Over we go. I'm going to graph it. Watch this. There's my 1 over 1 minus x. And look at that. All of a sudden, I'm getting closer and closer and closer. Now, this is where I have my error, right? This is where I'm missing. This is extra. But this is a heck of, I mean, think about that. That's only, what, 6 terms in? And I'm getting real close. So it's almost as though over here, if I let n go to infinity, there is going to be no difference between these two curves. They are going to be exactly the same. You will not be able to differentiate them from each other. You'll be able to differentiate them, strangely enough, but not from one another. And that's on the interval from -1 to 1. Anywhere else, this doesn't work. If I throw in a 17, it ain't going to work. They're not going to be the same. All right? Now, the cool thing is I can apply that to any other functions too. Let's try this one. How about f of x, how about f of x equals 1 over 1 plus x squared? Now, oh, dang, that just smells like something we've seen before. 1 over 1 plus x squared. That looks like something interesting. Well, we won't go there yet. Boy, it's almost in the same form, isn't it? S equals, for a geometric, a over 1 minus r. A over 1 minus r. If I could only manufacture an r, or a minus r, let's see. So how about 1 over 1 minus negative x squared? Wouldn't that do it? Now look, a is still 1. It appears that r is equal to negative x squared. So 1 over 1 plus x squared appears to be equal to the sum, geometric. All I'm doing is geometric here, you guys. I'm not doing anything fancy. That's supposed to be a sum, not a backwards 3. As n goes from 0 to infinity of a, which is 1, times negative x squared to the n. This whole thing turns into the sum, as n goes from 0 to infinity, of -1 to the n times x to the 2n. Crazy. Now, watch this. This is the coolest part. Watch. All right, let's just list some terms and see what happens. My first term is a 1. We knew that because that's what a was. My next term, what's my next term going to be? It's minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, etc. That should be a minus, right? Etc., etc. What do you notice about this series? It's alternating. The cool thing about this, if I were to graph this, and graph a whole bunch of terms of this, if I wanted to know what the remainder or the error was, remember over here, the difference between the actual curve itself and the polynomial that is approximating the curve, remember from alternating series tests back when we learned about ratio tests, we know that the remainder, the error, is always going to be less than b sub n plus 1. Oh boy, it's all coming together now, isn't it? Another thing, so let's write that up. Hold on, let me kick over here. I know that 1 over 1 plus x squared, which is equal to the sum, as n goes from 0 to infinity, of -1 to the n times x to the 2n. Because it's geometric, remember, a equaled 1 and r equaled negative x squared, right? Because it's geometric, and I know geometric series only converge to 1 over 1 minus, a over 1 minus r when absolute r is less than 1. I know that this guy will converge to this guy when the absolute value of negative x squared is less than 1, which is, remember, absolute values get rid of negatives, so this is absolute x squared is less than 1, which implies, if you think about it, this is going to be true when x between -1 and 1. Isn't that awesome? That's just awesome. Now, let me take you through a little trip on this one. This next one's going to take a little thought. How about this? How about f of x equals, let's go x squared over 3 plus x. All right? And remember, we're trying to build this guy and from n equals 0 to infinity of a r to the n. Okay? Well, the very first thing that I notice is I got a 3 here. And I need, if you look close, that's a 3, that's a 1, that's a plus, that's a minus. Well, I'm not afraid of the plus part, right? Because we used that trick before, but that 3 scares the bejesus out of me. But if I look close, can't I rewrite this as x squared? Whoops. X squared over, I'm going to factor the 3 out. So I'm going to leave this as 1/3. And then in the denominator, I'm going to write this as 1 plus x thirds. Right? If you don't believe yourself, redistribute the 3 back, and you'll get x squared over 3 plus x. So I'm going to ignore the 1/3. I'll deal with that at the end. I'm going to rewrite this as, well, I'm not going to ignore it yet. I'm going to write it as 1/3 times x squared over 1 minus negative x thirds. Guess what I got? Ignore the 1/3 for just a sec. Bear with me. We'll just deal with this guy. All right? A, notice A, I'm just going to let A be x squared. I'm going to let R be negative x thirds, right? Which implies that this comes from that x squared over 1 minus negative x thirds is equal to A and R, right? The sum as n goes from 0 to infinity of x squared, that's just A, times R to the n, which is negative x thirds to the n. Now, let's clean this up just a little bit. Watch how this works. This is going to turn into the sum as n goes from 0 to infinity of, that's going to be, there's a constant there. Do you see that this is negative 1/3 times x? And since it's raised to an exponent, that exponent operates on both of those terms. So I'm going to go negative 1/3 to the n times, now think about this. Let's change colors again. Think about this. I'm left with an x squared times x to the n. Well, what is x squared times x to the n? The bases are common. When I multiply terms with common bases, what do I get? I get the sum. So this is x to the n plus 2. Now, we're not done yet. We're close. Remember, we had a 1/3 that we pulled out of here. So this implies that 1/3 times the sum, as n goes from 0 to infinity, of negative 1/3 to the n times x to the n plus 2. Now that 1/3 is out in front, but remember, this is just a sum. So the distributive property is in full effect. I'm going to rewrite this guy as the sum as n goes from 0 to infinity of. Now careful, again, let me change colors so we can see what's going on here. Think of this as negative 1 to the n times 1/3 to the n. So 1/3 to the n times 1/3, whoops, 1/3 to the n times 1/3 is equal to 1/3 to the n plus 1 times negative 1 to the n. I love me some negative 1 to the n's. You know why? Because it creates an alternating series. And the error bounds on an alternating series are so easy to find. It's just b sub n plus 1, right? If I go out to the 5th term, then the 6th term is going to be my error, which is fabulous. Okay, let's see. It's back to the n. Where am I? And this is times x to the n plus 2. And we know that this equals x squared over 3 plus x. Now, when does it equal that? Let's turn back to black. When does it equal that? Well, remember, r, it's not incidental that I used a little r, has got to be, absolute r has got to be less than 1. So this is when absolute negative x thirds is less than 1, which implies that absolute x is less than 3, which implies that x is between negative 3 and 3. So much fun. Nothing to it. Okay? So this is going to be true. This function right here is going to equal this power series so long as x is between negative 3 and 3. But furthermore, here's the coolest part. Okay?